In our previous lecture, we introduced the concept of passivity, which applied to systems that have same size inputs and outputs. Okay, and then having introduced passivity, we talked about some real-life examples that we're more or less familiar with that are passive. Okay, in this lecture, we will study the relation between passivity and stability of the origin of a passive system when the input of that system is set to 0. Okay, we start with the first lemma, okay, which tells us that which has a very simple statement and also very simple proof. The proof directly follows from the definition of passivity. Okay, so if the system x that equals xu y equals h xu is passive, okay, with positive definite storage function v is a function of state, slightly outbound function. Okay. Then the origin of the unforced system by which we mean the system x that equals f of xu when the input u is set to 0. So it's identically 0 for all times, and then this system in that case becomes the x that equals f of x type autonomous system, and then the stability of the origin of that system is guaranteed when this condition is satisfied. Okay. The unforced system x that equals f of x 0 is stable. That is, solutions starting close to the origin remain close to the origin for all future times. And the proof directly follows from the definition of passivity and positive definiteness of the storage function. We note that the standard definition only requires that the storage function is a positive semi-definite function of the state. Okay. So with a little bit stronger condition where the storage function is positive definite, then when u is set to 0, the origin of the reduced system has to be stable. Okay, here is the proof. Okay, the definition of passivity says that v dot rate of change of the storage function along the solutions of the system is never larger than the inner product of input and output. U transpose y. Now we consider the case where u is identically 0, so that implies that v dot is less than or equal to 0, no matter what the output may be. Okay. What else we have? V positive definite, and v dot is never positive. Okay. Therefore, by Lyapunov's theorem, the origin has to be stable. Okay. The origin is stable. Okay. So that's a very short proof of our first result. Now, obviously, an interesting question is, how about asymptotic stability? Okay, what can be said about asymptotic stability? And our next result, okay, the following results will be about asymptotic stability of the origin when the input is set to 0. Okay, so for that, just passivity will not be enough. We will require some further conditions like strict passivity or output strict passivity. Okay. Now, the next result, it's lemma 6.7 from the text, is about the asymptotic stability of the origin of the unforced system under strict passivity. Okay. Lemma 6.7a. And in lemma 6.7b, we'll be talking about the output strict passivity case. If the system x that equals f of xu, y equals h xu is strictly passive, then the origin of x that equals f of x0 is asymptotically stable. Okay. By the way, we'll always be dealing with the systems that satisfy when both arguments are 0. Then both functions f and h are 0. Therefore, the origin of the unforced system is an equilibrium point. Okay. Then the origin of the unforced system is asymptotically stable. Furthermore, okay, if the storage function is radially unbounded, then we have global asymptotic stability of the origin. If the storage function is radially unbounded, then the origin is okay, the origin of the unforced system is globally asymptotically stable. Now, at first sight, especially when compared to our first result, it seems that there's something wrong with lemma 6.7, because even for stability, we had to require that the storage function is positive definite. But now we're after a stronger result, namely asymptotic stability of the origin. But for that, we're not requiring, okay, positive definiteness of storage function explicitly in this table. Okay. Now, it turns out that there's nothing wrong with that statement, because from the things that we are already assuming, positive definiteness of the Lyapunov function follows as a consequence. Okay, so it comes for free. It comes for free because of this strict passivity. Okay, but that's not obvious, so we have to establish that. So strict passivity will imply that the storage function is positive definite, and then for the time derivative of the storage function, which is positive definite, we will have v dot less than or equal to minus some positive definite function of the state. That's because we're talking about strict passivity, and that comes by definition. And then we have by Lyapunov's theorem a split stability of the origin. Furthermore, if the storage function is radially unbounded, we have again, and not by some version of Lyapunov's theorem, we have global asymptotic stability of the origin. Okay, so let's therefore remember the definition of strict passivity and follow, and we will proceed from there. Strict passivity means that the inner product of input and output is never less than v dot, okay, inner product of the gradient of v, okay, with the right hand side of the system, okay, f xu, plus some positive definite function of the state, okay, psi of x, with positive definite psi. Okay, so it turns out that positive definiteness of that psi must be inherited by the storage function V, okay, which appears in the definition of strict passivity. So we're talking about what we consider the case of the unforced system, that is when the input is set to 0. So this implies what? When input is 0, when u is 0, this becomes 0 regardless of y. Okay. And then what we have is, this is v dot, okay, for the system x that equals f of x0. So v dot is less than or equal to, we throw this guy to the other side, minus the psi of x. Okay. So v dot of x never greater than minus psi of x. Since psi is positive, this thing here, minus psi, is clearly negative definite. So let's call this inequality 1. Okay, it will be the key inequality in order to establish the result. So here is the claim that we will need to establish the final result. Inequality 1 implies that V has to be positive definite. Okay, a positive definite function of the state x. Here is the proof, okay, because we're going to prove it by contradiction. Let phi t eta be known solution, okay, of the unforced system x that equals f of x0 starting from the initial condition eta. Okay. Well, usually we use the notation x of t, but now it's important to indicate explicitly what the initial condition is in our notation. So we switch to, therefore, this a little bit more complicated notation. Okay, so this is the solution. The solution of x that equals f of x0 starting from the initial condition eta. Okay, that is, since we're dealing with a time invariant case without loss of generality, we always take the initial time to be 0. So what we mean by this notation, therefore, is at the initial time, which is t equals 0, the solution is eta. Okay, so this eta is just initial condition for the solution. So what we're going to do is we're going to integrate both sides of inequality 1. Let us integrate inequality 1. Okay. So we integrate it from 0 to some later time, and that later time, let's call it capital T. So if you do that, what we have is v of phi minus v of phi 0 a. Okay, so we're integrating from 0 to capital T. Since the left hand side is beta, what we have is v, the value of v at time t, and value of v at time t equals 0. And this is less than or equal to minus from 0 to t psi phi t eta dt. Okay, now since this is just the initial condition, this thing is eta, therefore we can simply write this expression in this shorthand form, okay, v of eta. And then, by definition of passivity, the storage function is positive semi-definite. Therefore, this cannot be negative. So what we're going to do is we're going to throw this guy to the other side and this to the left-hand side, and we're going to remove that because it's never negative. Therefore, remove that to not affect the inequality, and we will have v of eta greater than or equal to this integral. Okay, dt. Let's call this inequality. Equality number 2. Okay, so once again what we did is, this is what we have as for v dot when input is 0, coming from the definition of strict passivity. So what we did is, we took this inequality, we integrated both sides, okay? This is the left-hand side, the value of v at time capital T, and the value of v at time t equals 0, the initial time. And the right-hand side is minus the integral of the state passed through this positive function psi. Now, since this is never negative, we can remove that, and the inequality will still be valid. Okay? And then we removed it, and then we just swap. We took this guy to the left-hand side, and this guy to the right-hand side, and you obtained inequality number 2. And now, this, it turns out, implies that the function v, the storage function, must be positive definite. Okay, suppose v is not positive. Okay, so what we're going to do is we're going to prove positiveness by contradiction. We're going to suppose otherwise, and then we'll reach a contradiction. Suppose v is not positive definite, then by definition there should exist some state other than 0, other than the origin, such that v eta is 0. Okay. Then the inequality that we just obtained here, called inequality number 2, implies the following: 0, 5 t eta dt equals 0. Now, why does it imply that? Okay, so this is 0. Okay, so this thing that we're integrating has to be less than 0. But the integrand here, psi, is a positive function. So it can never be negative. Okay, so integrand is never negative, and you're integrating something that's never negative. Therefore, this can never be negative. Okay, the integral can never be negative. So that means the integral must be greater than or equal to 0. So this integral is therefore less than or equal to 0, and also greater than or equal to 0. And there's only one thing that it can be equal to, and that's 0. Okay, so the integral must be 0. So that implies what? That implies that the, excuse me, 5 t eta equals 0 for all t in 0 to t. Okay? Now, psi is a positive definite function of its argument, okay, and then you integrate that, you obtain 0. Therefore, since this can never be negative, the integrand at all times from 0 to capital T must be 0. So if the integrand is always 0, and this function psi is a positive function, therefore the argument of that function psi must be 0, okay, identically, from time t equals 0 to t equals capital T. Okay, so this solution must sit identically at 0 at the origin for all t between 0 and capital T. Because psi is positive definite. And why psi is positive definite? Because we are assuming that the system is strictly passive, so that comes by definition. Now, since this is 0 for all t 0 to capital T, clearly it's 0 for t equals 0 initial time. So let's evaluate that. Okay, so this is 0 for all t. Clearly, it has to be 0 also for t equals 0. And at t equals 0, it's nothing other than the initial condition, which is eta. Okay. So, what we have therefore obtained is, we start from the assumption that V is not positive definite. And there should exist an eta different than 0, for which the eta equals 0. But then the consequence of that is eta equals 0. Okay, so we start from eta not equals 0 and we reached eta equals 0. Therefore, that's a contradiction. Hence, V has to be positive definite. But eta is different than 0. Okay, so that's a contradiction. Hence, V is positive definite. And once we have positive definite, we have everything to result follows y, because, okay, let's end the proof. Finally, V is positive definite, and we have that V dot less than or equal to minus psi of x. Psi is positive definite, therefore minus psi is negative definite. So we have a positive function whose time derivative is less than or equal to a negative definite function. So that means the origin is asymptotically stable. Okay? Furthermore, if V is radially unbounded, we have from Leopold's theorem, one of Leopold's theorems, global aspect stability of the origin. And V radially unbounded implies global aspect stability of the origin. Okay. So, what we have covered so far is, first, if the system is passive with a positive definite storage function, then the origin of the unforced system is stable. Second result, if the system is passive, strictly passive, okay, then the origin is of the unforced system is stable. Furthermore, if your storage function is radially unbounded, the origin of the unforced system is globally stable. Now we will extend these results, extend these results to the case where we have, instead of strict passivity, output strict passivity. Okay. So the question, therefore, that's meaningful to ask at this point is, how about output of strict passivity? That is, Does output strict passivity imply that the origin of the unforced system is asymptotically stable? The answer is not necessarily. So something further has to be assumed in order to obtain asymptotic stability. Okay. Not necessarily. Okay. We further need some sort of observability condition on the output. Observability property. Okay. Now, to get some ideas or to get some clues about what we should assume, okay, to reach asymptotic stability of the origin, starting from output passivity, we have to, let's very quickly review observability for LTI systems. Okay, usually LTI systems are a good first stop to get some ideas for the nonlinear situations. So we call that LTI system x equals ax plus b, but now we're considering the u equals 0 case, so let's forget about that and consider this autonomous case, x equals ax and y equals cx, the output. So this is the linear input-free system, okay, with output y equals cx. Now this system is observable if, okay, the definition of observability is that by looking at the output, the evolution of output, y of t, okay, so you don't just know the output at some particular time, but you know the output, you can measure the output, let's say, throughout some interval, okay. If the system is observable, then no matter how small that interval is, you will be able to figure out the state, the initial condition of the state, but since you know the model, once you know the initial condition, you can figure out the entire state, okay. And we have plants, we have systems that exactly do that. That is, by looking at the output information, they construct an estimate of the state, and such systems we call the observer systems. Okay, the simplest example being the Leuenberger observer. Anyways, so by looking at the output, if we can figure out the state, then that linear system is said to be observable. Now that definition has many is equivalent to many different conditions, okay? So all those conditions are equivalent for the linear case, okay? But for non-linear case, they may not be equivalent, or they may not even be meaningful. For instance, if it's a condition in terms of eigenvectors, it's meaningless for non-linear systems, because we don't have eigenvectors for non-linear systems. Anyways, so let's remember some of those conditions. One condition is that you construct a matrix, okay, observable matrix, and you check the rank of it. That's one condition, okay? So it's not really useful for our case, for the non-linear case. We don't want to deal with any matrices. Another condition is that system is observable if and only if no eigenvector of A belongs to the null space of C. Again, no use, because we don't have any eigenvectors for the non-linear system. Now, another equivalent definition is the one that we're gonna be using. So this system is observable if and only if identically zero output implies identically zero state, okay? or more technically, you check the output at some interval. During some interval, delta is larger than 0. It can be arbitrarily small. It can be a very, very tiny interval, but nevertheless it has to be interval. The delta cannot be 0, that is. If the output is 0 in that interval, throughout that interval, and if the system is observable, and only if the system is observable, then the state necessarily must also be at 0. Okay, so this definition is the one that we will adopt to put forward our observability condition or observability definition for the nonlinear system. Okay, where delta is arbitrary. Okay, and this will motivate us for the following condition. This is our observability definition for nonlinear system. Okay, definition 6.5 in text. We're going to call it ZSO property for short. Okay, this stands for zero state observer. The system x that equals f of xu, y equals h of xu is said to be zero state observable if for all delta positive and all solutions x of t of the unforced system x that equals f of x0, we can write x of t belongs to z in Rn. Okay. N is the dimension or the order of the system. Hz0 equals 0. So this is simply the set of the state, okay, set of states for which the output is 0. Okay. Now this is that set, and now x of t belongs to that set, not at some particular time, but throughout some interval. For all t in 0 to delta. Delta is something, some positive number. This is equal to x of t equals 0 for all times throughout the same interval. Okay? If these two things are equivalent, then we say that the system is zero state also. And now, this condition, it turns out, is what we need in order to obtain a split stability of the origin of the unforced system from output strict passivity. Now we can write down a statement of the second part of our lemma 6.7, lemma 6.7b. Remember that lemma 6.7a was the part where we dealt with strict passivity. If the system equals f of x u, y equals h of x u is output strictly passive. And zero state observable. Then origin of the unforced system. Zero is asymptotically stable. Okay, and as was the case with lemma 6.7b, if we further have radially unboundedness of the storage function, then we have global asymmetric stability of the origin. Furthermore, if the storage function is radially unbounded, then the origin is globally asymptotically stable. Okay, let's down proof once again. Observe that we don't make any positive definiteness assumption on the storage function. So, as was the case with lemma 6.7a, we will somehow have to obtain that positive definiteness property of the storage function from the conditions that we assume hold, which are output strict passivity and zero state observability. So, together output strict passivity and zero state observability must yield positive definiteness for the storage function. So that will be the first part of our proof. Okay, first let's list down the conditions, okay, that we have in our disposal. U transpose Y So this is the definition of output strict passivity. Okay, the inner product of input and output is never less than V dot, where V is the storage function, plus this positive definite function of the output. Okay, so we have Y transpose times rho of Y. Rho of Y is a vector. Okay, it's same size as the output. Therefore, this inner product is meaningful. Therefore, it's a scalar. And the property of rho is such that this is always positive, provided that Y is different than 0. And for Y equals 0, clearly it's 0. Therefore, here we're talking about a positive definite with respect to Y function. Okay, so that's output strict passivity. And now we're considering the case where the input is 0, U equals 0. When U equals 0, this becomes 0. This is V dot, and what we have is V dot less than or equal to minus Y transpose rho of Y. Okay, this is our inequality 1 for the proof. Okay, now we claim that inequality 1 plus zero state observability implies positive definiteness for the storage function V. 1 plus zero state observability yields V is a positive definite function of state. So let's prove that claim. here is why that claim is true, because we're going to approach the problem from the same angle that we did for proving positive definiteness in the case where the system is strictly balanced. So we will use the old notation phi t of eta, denoting the solution of the unforced system. X that equals f of x 0 with initial condition eta. Okay, starting from eta. And as before, we will integrate inequality 1. Okay, integrating inequality 1, and what we have is on the left hand side we have v of phi of t eta minus v of phi of 0 eta, and this is eta, therefore this is v of eta, and on the right hand side we have minus 0 right hand side we have minus integral of from 0 to t y of t transpose times rho of y of t. Now what's y of t in terms of the solution? Phi, it's here, okay? Y of t equals h of phi of t eta, comma, u of t, but u is 0, okay? So therefore what we have here is h transpose phi t eta times rho of h of phi t eta. Excuse me. H of t eta, and the input is 0, so now we can close parentheses and that dt. So basically here what's written is y of t transpose times rho of y of t. Okay. Now this v by definition is a semi-definite function. It's our storage function. It's never negative, therefore we can remove it and the inequality will still remain valid. That's what we do. We remove that and then we take this guy to the right hand side, this guy to the left hand side. And what we're left with is v of eta greater than or equal to 0 t. Here we wrote v of eta because eta, excuse me, phi at t equals 0 is initial condition, which is eta. V of eta greater than or equal to h transpose phi rho h phi. So here there should be a 0. Okay. Likewise here there should be a 0. Okay, so this is our inequality 2. Now, so far we haven't yet used zero state observability, but it's now we're coming to a place where we will invoke it eventually. Now, suppose, as before, we're going to use contradiction to prove our claim that V is positive definite. Suppose V is not positive definite. Okay. Then we can find a non-zero initial condition, okay, eta different than 0, such that V of eta nevertheless still is 0. Then the inequality 2 will imply the following. Then inequality 2 will imply that. Okay. So v of eta equals 0. So this integral is less than or equal to 0. Okay. And also this y transpose rho of y is a positive definite function with respect to y. Okay. So therefore the integrand is never negative. Therefore the integral is never negative. That means this whole thing is greater than or equal to 0. So this thing here is less than or equal to 0 and also greater than or equal to 0. Therefore, the whole thing must be 0. So the integral is 0. And this, what we're integrating, is never negative. Therefore, the integrand must be identically 0 throughout the interval t equals 0 to t equals capital T. And then this integrand is 0 only when y equals 0, because it's a positive definite function with respect to y. Therefore, throughout the interval from 0 to capital T, this phi passed through the function h must be identically 0. Okay. So 2 implies h of phi of t eta, comma 0, identically 0 for all t between 0 and capital T. Now we can use zero state observability. This implies phi t eta. Okay, the solution starting from the initial condition eta must be identically 0 for all t in 0 t. Okay, from this line to that line, what we have used, we use zero state observability. Okay, and therefore, if this is true for all t, clearly it's true for t equals 0. Plug in t equals 0, and that gives you eta. Okay. Eta must equal to 0, which contradicts our initial assumption that, which was eta was different than 0. Contradiction. Okay. 2 eta different than 0. Hence, our claim must hold true. That is, v is or has to be a positive definite function of the state. Okay, now let's return to the decrease inequality or the decrease condition that we obtained, which was inequality 1. We turn to inequality 1, which was v dot less than or equal to y transpose rho of y. Now let's consider the case. Clearly, it's not a negative definite function of the state. Okay, it's only negative semi-definite. So let's consider a case where the v dot is identically 0. So v dot identically 0 implies that y of t is identically 0. Okay, because this function is a positive definite function with respect to the with respect to y. Now this implies x of t is identically 0. And the reason that we have this implication is because the system is zero state observable. Okay, 0 output throughout an interval means 0 state by 0 state observed. Hence, we have obtained the following. A. No solution except the one that sits at the origin. Okay, that is x of t identically equal to 0, can identically, by the way, this identically means just for all times, identically stay in the set where time derivative of the storage function is 0. B, the storage function is positive definite. Okay, and now what we're going to do is we're going to invoke invariance principle, a very useful tool by LaSalle to establish asymptotic. So 1 plus A plus B. Okay. 1 is this, the decrease condition, and then A is this invariance condition. Then B is positive. Implies origin is asymptotically stable by invariance principle. 1 plus A plus B, and plus further that B is radially unbounded. Okay. We have origin is globally stable, again by invariance principle. Okay. So this was, if you're interested, it was corollary 4.1. So that's where we stated that result earlier, and this is another version, corollary 4.2 from the text. Okay. Those of you who are interested, go and check those results once again. And that completes the proof. Okay. Once again, what we have proven is if you have a system that's output strictly passive, and the origin of the unforced system is asymptotically stable if the system is zero-state observable, and also if you have that condition plus radially unbounded storage function, then the origin has to be globally asymptotically stable. Okay, now let's apply our last result to a simple example so that we can gain a little bit familiarity with it. Example. Second order system, x1 that equals x2, x2 that equals minus a x1 cube minus k x2 plus input, and the output of the system is the second state variable. Okay, y equals x2. And we assume that the parameters a and k are positive constants. Okay. For the storage function, v of x equals 1/4 a x1 4 plus a1/2 x2 squared, which clearly is positive definite and radially unbounded. We have v dot equals a x1 cube x1 dot plus x2 dot. x1 dot is here, x2 dot is here. Okay, so let's write them down. So we have a x1 cube x2 plus x2 times minus a x1 cube minus k x2 plus, okay, so that's find the derivative of the storage function along the solutions of the system. We have this cancellation, okay, and what we're left with is minus k x2 squared plus x2 u. Therefore, we have V dot equals minus K times, remember that the second state variable is the output, y squared plus y times u. Therefore, this system is, since it's a positive function of the output without the minus sign, this system is output strictly passive. Okay, output strictly passive. And now let's figure out whether this system is also zero state observable. If it is, then output strict passivity plus zero state observability will guarantee that under the unforced conditions, and when you set u equals 0, then the origin of the unforced system is globally asymptotically stable. Why global? Because the storage function is radially unbounded. Okay. So let's therefore check zero state observability. So when we consider the unforced case, the input is set to 0. Zero state observability says that set the output to 0. Okay, so output is 0 identically. And in that case, input is also 0. In that case, check whether the state also is identically 0 or not. Okay, suppose we consider in this case, somehow y of t is identically 0. So that means x2 of t is identically 0 because our output is same as the second state variable. Now x2 of t is identically 0 means that, okay, so it's a constant signal, clearly its time derivative will also be 0. x2 dot of t is identically 0. What's x2 dot? Okay, now x2 is identically 0, x2 dot is identically 0, u is 0, identically 0, therefore we have minus a x1 cube, okay, or x1t of x1t cube, and that's identically 0, and that's only possible when x1 of t is identically 0. x1 of t is identically 0. So what we have therefore is, when output is identically 0, both state variables has to be identically 0. In other words, the state is identically 0. Therefore, this system is zero state observable. Zero state observable. Okay. And now we can say something about the stability of the origin of the unforced system. Okay. We have output strict passivity for our system. We have zero state observability, which we have just shown for our system. Plus, we have radially unbounded storage function. Okay. And those three conditions together imply that the origin is globally asymptotically stable.